Good evening, everyone. Are you able to hear me? Can anyone please
Yes,
confirm?
sir.
Is my voice audible?
Yes, sir.
Hello.
Yes, sir. Yes, sir.
Can anyone please confirm? I am not being able to hear anything.
Yes, sir. Yes, sir. Hello.
Okay. Okay. It's audible from my side. Okay, just give me 1 minute. My writing pad is not working properly. Just give me 2 minutes. I'll fix it.
Hello, hello. Hello, hello, hello.
Okay, good evening everyone. Sorry for the delay. My writing pad was not working properly. So we'll start with our fifth session today. Are you people able to see the slides?
Yes, sir.
It's visible, right? Okay, so we'll begin with the live session 5. The course is Natural Gas Engineering. So we'll be solving today week 5 assignment. The tutor for this course is Dr. Pankaj Tiwari. He is from Department of Chemical Engineering, IIT Guwahati. And I am myself is Vishal Dhar. I am the TA for this course, and I am also from the IIT Guwahati Chemical Engineering Department. So we first of all will go through a quick revision of quick 5 contents. The quick 5 is mainly about separator and its design. So
Hello, sir.
yeah,
Hello.
hello.
Can you slide show it? Means it will be beneficial.
Okay. Is it okay now? Hello.
I am not able to see it. Slide show.
Just, just say if it's if full screen is coming now.
Sir, you can go because it is not happening.
Yeah, there is some problem. Even
No,
classes
no
back
issue, no
also.
issue.
The slides are visible, right? The writing in the slides are visible, no?
Yes, sir. Yes, sir.
Okay, then we'll go like this because we have already wasted a lot of time today. So, what are separator functions? Primary phase it is an instrument for mainly primary phase separation, defined phase, liquid from gas. So it separates liquid hydrocarbon from gas. It also refined by removing entrained liquid mist from the gas. The liquid mist that are present in the gas droplets are also separated. It also separates the entrained gas from the liquid. The gas bubbles that are trapped in the liquid are also separated, and separate discharge of gas and liquid which are not entrained. Different means without entrainment, if there is gas and liquid, it also gets separated. So separator components, there are different types of components in the separator. First is the centrifugal inlet device. It helps in the primary separation of the liquid and gas. Second is large settling section of sufficient height and length. The settling section is the main section of the separator, which takes the main space of the separator. It allows liquid droplets to settle out of the gas stream and provides adequate surge room for slugs of liquid. Next is, see, I won't go into the details of everything because you already have been taught this in your class, so I'll just go through quickly. Next is mist extractor or eliminator near the gas outlet. It coalesces small particles of liquid. Small particles of liquid coalesce and form big droplet of liquid, and with the help of gravity, they fall into the liquid section. The other parts that are present in the separator are level controller, liquid dump valve, gas deck, pressure valve, safety relief valve, gauge glass, instrument gas regulator. So, the selection of separator depends on three factors mainly: characterization of the production stream to be treated, if it is a gas well or oil well or oil and water well, whatever the case is. Next is floor space availability at the site. The space available at the site dictates what kind of separator we'll be using: spherical, vertical, horizontal, whatever may be. Next is the cost. There are mainly three types of separator in use in the fields these days: vertical separator, horizontal separator, and spherical separator. Vertical separator used for liquids having intermediate gas-oil ratio, having large slugs of liquid, and they occupy less area but are costly. Second is horizontal separator. They are widely used for high gas-oil ratio wells where the gas quantity of gas is very high. Then it has a much greater gas liquid interface, and horizontal double tube separators are also present. They are low cost and they have high liquid capacity. Then there is, it should be spherical separator. Spherical separator, it is an expensive and compact separation arrangement where the area is very less. We use spherical separator, but mainly we use vertical and horizontal separator all over the world. It is used where the area is less, very limited surge space and liquid settling space available. Liquid level control in this type of separator is very critical. There are I have different types of separator. First one is this one is vertical separator. Second is horizontal separator in this picture. This is the third spherical separator. Again, then there is three-phase separator for separating oil, water, and liquid. So, what is three-phase separator? So, oil, gas, water, three-phase are commonly used for well testing and in instances where free water readily separates from oil or the condensate. It is mainly used where there are three phases are present: oil, water, and liquid. Three-phase separator can be accomplished in any type of separator. Any type of separator can be modified and made into a three-phase separator. Then three-phase separation feature is difficult to install in spherical separator because of the limited space. So as I told earlier, mainly horizontal and vertical separators are used because spherical separators are very hard to operate. They are only used in areas where this area space limitation is there. So what are the factors that affect separation? Separator operation pressure or temperature are the main two components that dictates the separation. Now, third is fluid stream composition and quantity. So when the operation pressure is very high and the operating temperature is low, we get high amount of liquid in the separator. To get huge amount of liquid in the separator or to increase the amount of liquid hydrocarbon in the separator, the pressure must be high and the temperature must be low, or the temperature must be low. Then there is flash vaporization calculation. These are done to get the optimum pressure and temperature that can be used to get maximum liquid hydrocarbon. Okay, flash calculations are used to get the optimum pressure and temperatures so that maximum liquid recovery can be achieved. Okay, now we'll go to the numericals. First question is a vertical separator under the following condition of oil flow rate of 2800 barrel per day with gas oil ratio GOR is 900 and operating pressure is 80 psi. These are the parameters given. First, we have to find the gas flow rate. Find the gas flow rate. It is very easy.
Sir, how to calculate that? Can you show that formula?
Yeah, okay, just so the Q is given as 2800 barrel per day. The GOR is GOR is gas oil ratio. Means for in part cubic feet of oil, how much gas we are getting? We are getting 900 cubic feet of gas, feet cube of gas for part feet cube of nine. Sorry, it should be barrel by barrel. So 900 barrel of gas we are getting from 1 barrel of oil. So this is if you have to find the gas flow rate, what will be the gas flow rate then? Just multiply these two. 2800 barrel per day. The unit is not given in the question now, so the unit will be just give me a second. It will be barrel per barrel. It will be standard cubic feet by barrel because the gas is measured maximum of the time gas is measured in cubic feet and oil is measured in barrel. So the unit for GOR will be SCF per barrel. Okay. So total gas flow rate will be 2800 barrel per day into 900 SCF per barrel. Barrel is gets cancelled out. Just multiply these two, you will get the answer. Anyone tell me the answer? Anyone? Just need to multiply these two. My voice is audible, right?
2520
2520.
000.
Yes, this is the correct answer. So the answer will be 2.5 mm SCF per SCF. Okay. So the option will be option C, right? The next question is the liquid settling volume. Find the liquid settling volume. The four options given are 49.20 barrel, 24.71 barrel, 10.67 barrel, and 1.94 barrel. I'm giving you the formula. The formula for that the liquid settling volume is W equal to W is the liquid settling volume. W is the flow rate and 1440 into this formula is already done in the class. I have seen the slides by T. For time, we will be taking as 1 hour, because as when it is not given in the question, take it as 1 hour or 1 day or whatever the question they are asking. For now, take it as 1 hour. The question should have been, I don't know who made the question last year. So question should have been the liquid settling volume per hour. So in 1 hour, how much liquid is settled? And W is the oil flow rate, which is 2800. 1443 is the conversion unit. You have to find G, and the time is 1 minute. Does anyone tell me the answer?
One 1.94.
So the answer is 1.9. So the correct option is D. Do let me know if you find any difficulty in understanding, or if you are not understanding any concept. I may not be able to clarify right now, but if there is anything, I can clarify in this class or the next class. Okay. So the third question is, a gas is flowing at a rate of 8 mmscf per day through a separator of diameter 1.8 feet. A condensate of API gravity 67-degree API is flowing at a rate of 25 barrel per mmscf. The operating condition is 850 psig and 78 degree Fahrenheit. Considering gas compressibility factor to be 0.8, Z factor is given as 0.8. K is a constant used in this type of numericals. K design constant. K value is given as 0.21, and the density of gas is 0.042 lb per feet cube, and density of liquid is 54.5 lb per feet cube. Determine the gas capacity at standard for a vertical separator. The four options given are 50.4 mmscf per d, 72.6. This is C. This mmscf d, it is written, but it is mmscf per day actually, but it is written like this only in all bits. So 72.62 mmscf per d, 115.60 mmscf per d, 150.95 mmscf per d. So what is the question? What do we have to find? Gas capacity. So the formula for gas capacity is, I will write down the formula. See, everything is given in the question. All the data, you just have to put all the data here. Temperature is given as 78 degree Fahrenheit. Then there is pressure equal to 850 psig. D equal to dia equal to 1.8 feet. Density of liquid is 54.2 lb per feet cube. Density of gas equal to 0.042 lb per feet cube. Then Z factor is 0.8 and K is given as 0.21. Put all the value in the question and tell me the answer. I want others also to respond. It doesn't mind if you are giving wrong answer or right answer. Just try to solve the questions and give the answer.
Ninety-seven point two six.
97 point.
Hello.
Yeah, hello. Okay, let me solve it. Let's see what answer comes. Your answer is 97.26, right? Point four.
96.26.
Okay, let me check.
96.26.
Okay, let me see what.
97 point.
Okay, see. If you solve this, you'll be getting answer as 115.8, which is equal to 116. Just check once. You might have done some mistake while calculating. So the answer, yeah, it is already given 1 point. You don't have to make it 116. The answer is 115.6. Okay. Just check once your calculation. You will do again. You will get the right answer. Okay.
97.26.
No, no, that answer is not correct. The correct answer is 115.8.
Okay, okay.
You can see my solution, right?
Okay, okay.
Yes, yes. Okay. So the next question is, a natural gas field is producing 125 SCF per day of gas of specific gravity 0.7. The wellhead pressure and temperature are 100 degree Fahrenheit and 480 psi respectively, and the fluid density and formation volume factor are 1.65 lb per feet cube. This is the density, and the formation volume factor is 0.034 feet cube per SCF respectively. The separator operating conditions are 170 psi and 105 degree Fahrenheit respectively. The mixture contains 0.5 weight% water having density of 62.1 lb per feet cube and viscosity as 0.63 centipoise, and 7 weight percent hydrocarbon liquid means oil, which is having density of 54.15 lb per feet cube and density viscosity is 0.78 centipoise, and the remaining is gas of density 0.68 lb per feet cube and kinematic viscosity of 0.012 centipoise. The hydrocarbon liquid hold up and search time are 25 minutes and 5 minutes respectively. Note down the parameters quickly.
So what is the formula?
Just write down the parameters now. After that, I will,
Okay.
because here no question is asked till now. They have only given the parameter. We'll go to the next question, then we will be getting what question they're asking. Okay, let me go to the question. The first question they have asked is the field mass flow rate. Not field, fluid mass. The fluid mass flow rate per hour at wellhead condition. You have to find the mass flow rate of the fluid. Means how many lb of fluid is produced per hour. The four options given are 0.3 into 10 to the power 5 lb per hour, 2.9 into 10 to the power 5 lb per hour, 7.1 into 10 to the power 5 lb per hour, 9.5 into 10 to the power 5 lb per hour. See, for this you don't need any formula, just you need conversion. See the question and someone is trying to yeah, for this question you this normal mathematics you need to do. Here it is given you have to find the mass flow rate, how much lb of fluid is produced per hour. See, the gas is producing 125 SCF per d of per day. It is producing 125 standard cubic feet. You have to convert this into lb per hour. Day we can convert in 24 hours, and for standard cubic feet you have to multiply it with. If we multiply it with Bg gas volume factor, then it will be 50. Standard cubic feet will cancel out and feet cube will be there, and again feet cube we have to multiply with density to find the convert it into mass. Did you get what I said? Let me do it. Just normal unit conversion. W equal to the flow rate is given 125 into 10 to the power 6 right? Into 1.65 is the density. Let me in conversion. W equal to 125 into 10 to the power 6 SCF per day into 1.6 is the density. Can you tell me the unit given? LB per feet cube. It will be 1.65 LB per feet cube into Bg. How much it is given? 0.034 feet cube per SCF, right? So here if you see SCF cancel out, feet cube cancels out. So how much it is? 125 into 10 to the power 6 into 1.65 into 0.034 LB per day. Again, we have to convert it into LB per hour. So it will be divided by 24 and it will be LB per hour. Just do the math and tell me the answer. Did you understand how I did the unit conversion here? Anyone please respond? Yeah, hello. Am I audible now?
Yes, sir.
Did everyone understand the unit conversion here? Can anyone please respond? Okay, for the answer for this will be, if you solve this, it will be 2.9 into 10 to the power 5 LB per hour. So the correct answer is B, 2.9 LB per hour. The next question is liquid flow rate at separator condition for water and hydrocarbon liquid respectively. See, it is a gas separator, mainly gas is coming, but with this gas, some amount of liquid, and in this question, if you see, 5%, 5 weight% water and 7.5 weight% water and 7 weight% hydrocarbon liquid are also coming in the separator. So we have to find the amount of liquid and amount of water and hydrocarbon that is coming in the separator. So for that, find the water flow rate. We have to find the how much 0.5% water is coming. So 0.5 by 100 into the flow rate of the hydrocarbon stream is just now we have found out 2.9 into 10 to the power 5 LB per hour. Just solve it and tell me the answer. My voice is audible, right? Can anyone please confirm? Hello? Hello?
Your voice is audible.
Okay, okay. Try to make this session interactive because otherwise I think the connection is lost or something. So the answer for this is LP per hour 1450, and the flow rate for the oil is same way, is given 7%, so it will be 7 by 100 into flow rate of the fluid stream 2.9 into 10 to the power 5 LP per hour. So if we solve it, it is 20300 LP per hour. So the flow rate of water is 1450 LB per hour and the flow rate of oil is 20300 LB per hour. So the correct answer will be option B. Next, we have to find the liquid mixture density at separated condition. The four options given are 101.15 lb per feet cube, 78.34 lb per feet cube, 57.26 lb per feet cube, and 25.87 lb per feet cube. Okay, I will do this directly because it is little tough. So in this question, we have found the flow rate of water equal to 1450 lb per hour. Flow rate of oil equal to 20300 lb per hour. Now we have to find the density of this mixture of these two. So for that, density of liquid equal to first 54.15, which is the density of oil, 54.15. What was the unit? LB per feet cube, I guess. Yes, LB per feet. 54.15 LB per feet cube, and the density of water is 62.1 LB per feet. So to find the density of the mixture, first we will be multiplying the density of oil with the flow rate of oil divided by the flow rate of both the liquids plus density of water into flow rate of water divided by the flow rate of adding the flow rate of both the liquids. Solve it. So if you solve this equation, you will be getting answer as 54.68 lb per feet. So correct answer is let me check once. Yes, 57. So the answer is coming as 54.68. This should be 54.68. There must be some typing mistake. So the correct option is C, 54.68. There is some typing mistake most probably. So the answer will be 54.68. Okay. So the next question is, if a mixed eliminator is added to the separator, the vertical terminal velocity is, we have to find the vertical terminal velocity. For that we have to, there should be constant, design constant should be given, which is equal to 0.308. So the formula for that will be vertical terminal velocity Vt equal to K root over density of oil minus density of gas divided by viscosity of, yeah, divided by density of gas. So density root over density of oil minus density of gas divided by density of gas into K. So the value of K is given as 0.308. It will be given in the question, into density of oil is 54.15 minus density of gas is 0.68 divided by density of gas is 0.68. Solve this question. So if you solve this, the answer should come as 2.73 feet per second. Okay. So the answer for this 2.73 feet per second is the correct answer. Next is the settling velocity of heavy fluid is assuming droplet size as 89 micron. We have to find the settling velocity of the heavy fluid. For that also we need a designing constant K, which have been given in the question. It will be 0.163. The settling velocity of heavy fluid is assuming droplet size to be 89 micron, which is, and Ka value is 0.613. The four options given are 2.05 inch per minute, 5.25 inch per minute, 7.54 inch per minute, and 10.98 inch per minute. So the formula for that will be VH equal to settling velocity of heavy fluid K into density of water minus density of oil divided by viscosity of water. Just let me check once. Yes, divided by not density of it would be viscosity of water. So everything is given in the question only. The value of K is 0.163 into density of water is given as 62.1 minus 54.15 density of oil divided by viscosity of water is given as 0.63. So if we solve this, the answer should come out as, just solve it and quickly.
Two point zero five, sir.
Yes, correct. 2.05. How many people are taking this course? Anyone knows? Hello. So the option is 2.05 inch per minute. How many people are taking this course? Can anyone tell me if anyone knows? Yes, no one knows that. Anyway, let us continue with the next question. The rising velocity of light liquid from the heavy liquid is for droplet size of 89 micrometer is four options given are 0.55 inch per minute, 1.66 inch per minute, 2.74 inch per minute, and 3.67 inch per minute. For this also K value will be 0.163. So the rising velocity VR equal to K into density of water minus density of oil by viscosity of oil. Just put all the values and tell me the answer. Viscosity of oil. All the parameters are given in the question. Tell me the viscosity of, tell me the rising velocity of the liquid, light liquid from heavy liquid. 0.163 K value is into 62.1. You people are able to understand my handwriting, right? Because it's very difficult to write in this writing pad. Okay, the 54.15 divided by viscosity is 0.78. Quickly tell me the answer. 0.163 into 62.1 minus 54.15 divided by 0.78.
1.66, sir.
Yes, 1.66, correct. Very good. So the answer for this is 1.66 inch per minute. Okay, so here we come to the last question. The settling time for heavy and light liquid through a settling distance of 1.5 feet and rising height of 0.8 feet. Four options. See, these all these numericals that we did today are very important for your exam. So try to try doing these numericals again at home because you will be getting similar numericals during your exams. Okay. So the settling time for heavy and light liquid through a settling distance of 1.5 feet and rising height of 0.8 feet. The four options given are 0.85 minute and 4.78 minute, 2.35 minute and 6.79 minute, 5.26 minute and 10.45 minute, 8.78 minute and 5.78 minute. So let me just quickly put in my title. For that, the formula of set for the settling time of heavy liquid, which is the formula is 12 into settling height divided by velocity of the heavy liquid. So it will be 12 into 1.5 is the 1.5 feet is the settling distance, and velocity of the heavy liquid we have already found out. 2. Settling velocity of heavy liquid is 2.05, right? So we'll be using this here. So it will be 12 into 1.5 divided by the settling velocity of heavy liquid, which is 2.05. So whenever you'll be getting such questions, you will be getting all the questions. There will be single questions, and these will be subparts. So if you do mistake in one question, then there are chances that the whole numerical will be 10, 15 marks numerical will be wrong. So be very conscious while doing such numericals. Okay. So the answer for this is 8.78 minute. And for light liquid, for settling time of light liquid will be 12 into H divided by velocity of the light liquid. H is the rising height. See, light liquid is the gas, so we are taking the rising height, and for heavy liquid it is oil or water. So we are taking the settling distance. As the water droplets or oil droplets settle from the mist extractor and the gas goes up, evaporates from the oil surface and goes up. So rising. So while calculating for light liquids, we will be taking the rising height, and while calculating for heavy liquids, we will be taking the settling distance. Careful. And the settling velocity or rising velocity of light liquid, we have already find out, it is 1.66. The rising velocity of light liquid. So we'll be using this here. So it will be 12 into 0.8 divided by 1.66. Tell me the answer. You will ask me. Tell me the answer quickly. See the answer for
5.78, sir.
yes, 5.78. Very good. 5.78 millions. So for heavy liquids it's 8.78, and for the light liquid is 5.78. So the option is D. Okay, so that's all for today. We have done the week 5 assignments. Thank you. So see you next Tuesday, same time. Is there any doubt you want to ask? Okay, I guess there is no doubt. So thank you. Good night.
Thank you, sir.